Okay. Any questions on the Grover search? What we discussed last time? We discussed all the steps of the algorithm. We showed that essentially Grover search works like it's a rotation in a certain two-dimensional space, right? So let me just take the first 10 minutes or so to recap Grover, especially the speed up part, as in the analysis of the algorithm itself. So if you recall, we are working in this two-dimensional plane where this is alpha, which is a superposition of the n minus m non-solution states, right? Where x is not a solution. Okay, and then this is beta, where beta is a uniform superposition of all the solution states. So there are m solutions, right? So this is a uniform superposition of the solution states. Okay, and we are starting out in a uniform superposition of all the states, right? So this is psi. Okay, I don't know whether I put a capital psi. Anyway, so psi is a uniform superposition of all the n computational basis states, right? But this then can be expressed in terms of the alpha and beta like this, right? And this is the angle we marked as theta by 2, right? So the starting angle with respect to the beta axis, so this is what I wanted to dwell on a little bit. So this angle, right, is what? This is, we can call it something else, maybe phi. Phi is basically cos inverse of square root m by n, right? So the starting overlap with the solution axis, so I'm going to call beta as the solution axis, right, is cos inverse square root m over n, right? That's where you're starting out. So this is what I will call the solution axis, and this is the non-solution axis. Okay, and what the Grover algorithm does is that each query, so each query to the oracle or each run of the so-called Grover iterate, right? Remember this G operation, which was basically this conditional shift, and I think we said that this is nothing but twice projection on psi minus identity. So it's first the oracle followed by this, right? And you're going to repeat this a certain number of times. Question is how many times, right? And that tells you what the query complexity of the algorithm is, right? So each run of the Grover iterate is going to rotate. So this is what it is. This rotates the state psi. I apologize for the background noise. It rotates the state psi by an angle theta, right? Where, remember, this theta now is related to where you're starting off with, right? This theta is related to this, this theta is the same theta. That's what I'm trying to say, right? Because this, I mean, the starting state is, of course, the uniform superposition, but depending on, first of all, how many solutions you have versus non-solutions, that's all basically decides how close or how far away you are from the solution axis. And every Grover iterate is going to rotate you by some angle theta, right? So let's say I've marked theta like this. So this is after one application of Grover, you're here, which is theta, right? Now let's say that after k applications of Grover, where are you? So now The question was how many times should we query the oracle in order to have a probability of, so let me just say success probability. Sorry. So in order to have a success probability which is greater than or equal to half. Okay. Now, what is a success probability? Success probability is basically what is your overlap with respect to beta. The mod squared of that, the amplitude of that is your success probability, right? So so what I had said last time was that if you do this Grover iterate a certain R number of times, I don't know whether I use this R. So if you repeat Grover R times, where R is basically the, let me just call it the closest integer function. Okay, I think that's a better way to write this. Cos inverse square root m over n by theta, right? So this is the claim that you need to do this so many times and then you will have a success probability greater than or equal to half. So I don't think I justified this very well. So I just wanted to justify this statement a bit more precisely and then also do the bound carefully. So what is this basically? So this cos inverse square root m over n is where you're starting with, right? That's your initial overlap. Then you rotate each time you're going theta closer to it. So ideally you want to rotate cos inverse square root m over n by theta, but that could be some, you know, irrational number for all you know, right? So you have to take the integer that is closest to it. Now, what does this closest integer mean? So let's say that this is an integer which is k, right? But the actual number is going to be k plus delta, where delta is between 0 and 0.5. So if this number turns out to be 1.5, you will round it off to 1. If it's anything greater than 1.5, you're going to say that it is 2. So it will be whatever is the closest integer to within a half error bar, right? So that's what this is. So the first thing I want to establish is that this indeed takes you to within, you know, a success probability of greater than or equal to half. So a success probability greater than or equal to half, remember, must mean that you must be within an angle pi by 4 of the beta axis, right? So so this is often what's called an angular error when people analyze this. So let's say that you have done this these many times. So let's say that this number is k, right? So the closest integer is k, right? K is an integer and this delta is something between 0 and 0.5. So let's say you've done this k times. Then we did this analysis the last time around that each time you rotate it, so with theta, this is going to 3 theta by 2, right? The next one will be 5 theta by 2. So if you do this k times, you will be at 2k plus 1 theta by 2. So this is where you are at. Okay. And this is after k iterations. So this is g raised to k, right? So this line, green line, is after k applications of g or k iterations of Grover. Okay. And what do I mean by the error? This indeed is what I mean by the error, right? So this angle, right, is what, okay, I've just put too many arrows, but this is the angular error. And the statement is that if you do this, if this k is the closest integer to cos inverse square root m over n by theta, then this angular error will be somewhere between 0 to pi by 4, right? That is the statement. So let me call this as theta e, okay, this angular error. So I can just call it epsilon. So this error, so if we rotate it these many times, the angular error is less than equal to pi by 4. Okay. So what is the angular error? Let's estimate that. So this error is going to be, you have done this now 2k plus 1 times, right? So this is whatever is this full angle, which is, where are we? So this cos inverse square root m over n plus theta by 2 minus this angle, right? G to the k. Now g to the k, it's too many, is theta. Let me say this, let me mark that also in green. So this big angle out here, right? This is 2k plus 1 theta by 2. Okay, I hope you follow. Every iteration is taking you to, rotating you by theta. So after k iterations, what will be the angle with this? That is 2k plus 1 theta by 2. So it's basically pi by 2 minus 2k plus 1 theta by 2. But I'm writing pi by 2 as the sum of these two angles. That is cos inverse square root m over n and theta by 2. Okay. So I hope this is clear, but at least you can look back at the notes and work it out again if it's not clear. So actually this whole thing is pi by 2, right? Minus 2k plus 1 theta by 2, right? Because this is where you are at after k iterations, okay? And now just using the fact that this delta is off from the integer to within 0.5, you can see that you can bound this by pi by 4, okay? So actually, wait a minute. So what is k plus? So the closest integer, let me say, is k. Okay. So this is k times. What is k plus delta? Is this exact number. So cos inverse square root m over n by theta is k plus delta. Okay. All right. So now let's do this. So this you can see various things cancel out. So this simply becomes cos inverse square root m over n minus k theta, right? And then that is nothing but, what is cos inverse square root m over n by theta minus k theta? That's just delta times theta, right? Which is basically bounded by theta by 2. But theta by 2 itself is bounded by pi by 4 provided m is less than equal to n by 2. Recall this, right? Therefore, your angular error is bounded by pi by 4. Okay, so this implies a success probability of finding a solution state, any solution state. This success probability is therefore greater than or equal to half. Okay, so I hope this idea is clear, and it is crucial for this that the number of solutions should be less than equal to n by 2. Okay, and all that we've used here is this idea of the closest integer function, and let me, if you want, call this equation as 1, and this simply comes from the fact that the Grover iterate each time rotates you by theta. So after k rotations you are here, and so this equality is basically using 1. Okay. All right, so this, I hope this is clear, and I hope where this is coming from, that if you rotate to within cos in the closest integer of this, you're within an error, you'll get a success probability of greater than half. You'll hit a solution after the measurement. You will get one of the solution states to within a success probability of greater than half. Okay, so the last thing that remains to be done is to show that this k is actually bounded by square root n over n, right? And that's a simple enough argument. That is basically, any questions on this error part, success probability part? Okay, so the final thing is, what is a bound on the query complexity? Which means what is an upper bound on this k, right? Remember, that this is the closest integer. So the closest integer is often denoted with square brackets. So this is cos inverse square root m over n by theta, right? And now cos inverse square root m over n itself is less than or equal to pi by 2, right? This angle that it's making with the beta, right? It's between 0 and pi by 2, this angle, right? Okay, so that is less than equal to pi by 2 theta, okay? And theta itself is greater than or equal to sine theta by 2. Oops, I'm going to say theta by 2. And sine theta by 2, right, is exactly equal to square root m over n, right? That's what this is. Remember, this is what we called cos, maybe I should start it, yeah. And this is what we call sine theta by 2, right? So sine theta by 2 is exactly square root m over n, and theta is always greater, at least in this range, theta is greater than equal to sine theta by 2, which is between 0 to, it's actually between 0 to pi by 4, right? And therefore, k is less than or equal to pi by 4 square root n over m, the closest integer, which is basically something of order square root n over m, right? Therefore, the query complexity goes as square root n over m compared to the classical query complexity. This is the quantum query complexity. Classically, this goes as order n. Okay, questions? All clear? Fine, then I mentioned how you can fix this issue of m being less than equal to n by 2 by actually augmenting the database, right? So if m is greater than equal to n by 2, right, then actually you're starting much closer to the solution state. And in that case, what happens is with successive rotations, you may actually cross this, right? Even a single rotation, you're going to cross this, right? And so your bounds will go a bit off, like how many iterations you need. It will actually tell you that you need more iterations, right? Which doesn't make sense. So the way to address that is actually by augmenting the database so that you now have more non-solutions than solutions, so that your theta by 2 is within pi by 4, etc., etc. So this entire analysis will go through, right? The final question is, okay, this is order square root n, but can you do better? So is there a quantum algorithm which can do better than Grover, right? So when Grover's paper came out, this was very nice. It was a quadratic speed up and so on. But the natural question that people have is, can you get exponential speed up, right? Can you have an even better scaling with respect to n in terms of the query complexity? So is Grover search optimal? So the answer is yes. And in fact, there was a paper that came out within a few months of Grover's paper where they showed that using a quantum oracle, you cannot achieve a speed up that is better than quadratic. You cannot do better than order square root of the size of the database, right? So this I am not going to discuss now. But what I will do is I will refer you guys to Nielsen Chuang, where they have a discussion of this. And yes, I still haven't decided your next assignment, but I might give this as an assignment problem, right? So I will refer, of course, all of this discussion, by the way, is all chapter 6 of Nielsen Chuang. I hope you have looked it up. I don't know whether I mentioned this earlier. So Grover speed up is all chapter 6 of Nielsen and Chuang. They even have a simple circuit for a search over a database of size 4. That's a 2-qubit Grover search, right? It's also nice to look at that example to see how the how the gate complexity actually is, especially for the oracle, right? So that is something also that we have not argued, but one can show that that is also polynomial in n. Okay, the gate complexity of the oracle. And finally, yeah, so no quantum oracle can do with fewer than square root n queries. So there is no quantum algorithm that can search with fewer than square root n queries. Okay. Yeah, the gate complexity. Let me also mention this. What about the gate complexity of the oracle? One can again argue that this is not very high. I had a precise statement about that, so I thought I would just mention that. So if you look back at the circuit, what did we have? Actually, let me just say not of the oracle, but of the algorithm itself. Okay. The oracle, of course, like I said, at the heart of it is the idea that whatever problem marks the solution state, that classical problem itself is easy to verify, right? It's only hard to search, but it's easy to verify, right? So what we need to worry about is actually the Hadamard's and the conditional phase shift. So the Hadamard's, we needed an n-qubit Hadamard, right? So this one can show requires something like log n operations. And then you have the conditional phase shift. Can be shown that this can also be done to within order n, right? So in all, this circuit complexity only scales as a polynomial in little n. Remember, little n is actually log of capital N, right? So this would be the gate complexity of this algorithm. I'm not making a rigorous argument here, but I just want to mention this, that this algorithm also wins out in this way, that it's not too hard to implement the Grover search itself. In the sense, it's not exponentially hard, and the search itself gives you a quadratic speed up in the query complexity. Okay. All right. No questions? Okay, so then let me proceed to the next. Yeah. Was there a question?
No, ma'am.
All right. So we'll proceed. So next.
I'm a little confused between query complexity and gate complexity.
Yeah, gate complexity means what is the complexity of implementing the circuit. So if you remember, the Grover circuit had this, right? So there was first an n-qubit Hadamard, then you had to do the oracle, then actually then you simply did the Grover iterate itself, right? Let me call this G, because the oracle is also a part of the Grover iterate, right? And this Grover iterate you had to repeat several times, right? Some k times, and then you measure. But this Grover iterate itself had the oracle followed by Hadamard tensor n, followed by conditional phase shift, just say phase shift, and then again a Hadamard tensor n. So these are all just boxes, right? So the way this query complexity works is that you don't worry about what is inside this black box. Okay. So this is what's called the black box model, right? So this black box you don't worry about. You simply ask, what is this k? How many times do I need to run this Grover before my measurement is likely to give me a solution with high probability? That is query complexity. But now if I start worrying about what is inside the black box, that is gate complexity or circuit complexity. Is the distinction clear now?
Yes, ma'am.
Okay, good. All right, so the Grover was the same class of algorithm as the Deutsch-Josa. They were all based on this black box or Oracle model of computation, right? So now we'll sort of change track and we will discuss the last main algorithm in this course. And it's also probably, if you understand the technique behind Grover and whatever we're going to discuss next, then you pretty much understand the basic logic behind most quantum algorithms that exist today, right? So the next thing that we're going to work towards over the next few lectures is the so-called holy grail of computation, which is the factoring algorithm, right? So we would like to work our way towards the quantum factoring algorithm. But then there are several steps that go into it, right? And we'll do this in a sequence. So the first thing that we will discuss in this sequence is the quantum Fourier transform. And there is again a whole class of algorithms based on the quantum Fourier transform. So the quantum Fourier transform will then lead us to the quantum phase estimation algorithm. This will then lead us to a certain number. So these are now the Fourier transform in itself, as we will see today. I don't know how much I will discuss, but I'll start doing it. In itself may not be that useful an algorithm, right? It's not solving anything. The quantum phase estimation is helping you estimate the phase of it's basically helping you estimate the eigenvalue of a unitary operator. And remember that eigenvalues of unitary operators are pure phases, right? So this is basically estimating the eigenvalue of a unitary operator. Again, you may ask, why is that useful? What computational problem does that solve? Well, it turns out that this solves something called order finding. Order finding is a certain number theoretic task, okay, which is at the heart of factoring algorithms. So this essentially is the root to factoring, okay. So what is at the heart of the factoring algorithm is basically this number theoretic task called order finding. And next week we may also do a little bit of number theory. Right now, of course, I'm not going to quiz you on all the number theory. That is just for information. But what you should understand crucially are these two things, which is the Fourier transform and the phase estimation algorithm. Because the phase estimation again is today used in various other contexts, right? Estimating the eigenvalue of a unitary operator and being able to do that efficiently with high probability. Okay. All right. So what is the Fourier transform? So the quantum Fourier transform is basically just an extension of what is in the classical scenario called a discrete Fourier transform, right? So this is just to tell you where we are headed with this Fourier transform. So let's first recall the discrete Fourier transform. So the input, if you wish, to a discrete Fourier transform is some string of this form, right? It's, let me just say it's x0, x1, x2, etc., xn minus 1. So let me just say there's a set of n complex numbers. I can visualize it as a complex vector like this, right? And what the discrete Fourier transform does is it transforms you from such a n-dimensional complex vector to another n-dimensional complex vector. So let me call this y0, y1, etc., where these y's are basically obtained by forming linear combinations of the x's with certain phase factors, right? So this is the exact transformation where yk is, so I said there are n of them, so let me say 1 over square root n sum over j going from 0 to n minus 1 e to the 2 pi I. Okay, there's too many It's too many indices here, but let me just write it and then again. So those of you who have seen Fourier transform in physics may view this as an integral, right? So you're used to writing maybe an integral of this form, which has a 2 pi xp, you know. So if I want to write this, let me just say xy by some basic measure here, and then you have your function f of x itself, and then you do a dx, and then you get a gy, right, with the complex phase here somewhere, right? So something like this. You call this k typically, right? Which is the Fourier space, but I'm just calling the Fourier space as y. Okay, so this is the original space, and this is what you may often think of as the Fourier space, right? Which in the case of, say, quantum mechanics, this becomes position and that becomes momentum. In the case of solid state physics, this may be the physical spatial lattice, that may be the reciprocal lattice. Those of you who have done signal processing and things like that, of course, know this very well, right? This is what you would call an input symbol set of complex numbers, and this will be the output, right? So this transforms some input complex vector to another complex vector, where the output symbols now are weighted by these phase factors, right? They are weighted sums of the inputs with these phase factors. Now, I, of course, here is a complex I. Those of you who are from electrical engineering, I know that you write this the other way around, in the sense that J becomes your complex, J becomes square root of -1. But for me, always I is square root of -1. J is an index running from 0 to n minus 1. K is another index running from 0 to n minus 1. And basically what you have here are some nth roots of unity, right? That's what these complex factors are, the phase factors are. So is this idea clear? You're just transforming one set of complex numbers to another, weighted by these phase factors. That's what a discrete Fourier transform does. And again, computationally, this is a very important and useful tool, right? Now, naturally, there's a way to extend this to the quantum setting, right? So we can define the quantum Fourier transform in an analogous way. So the quantum Fourier transform is a natural extension of the discrete Fourier transform, and not so much the continuous Fourier transform that maybe most of us from the physics background are probably more used to, right? So what the quantum Fourier transform does is it takes an orthonormal basis of an n-dimensional space. Of course, eventually we'll make capital N to become 2 to the n, so that you then have n qubits and so on. So it's an n-dimensional space. Let's call this orthonormal basis. Let's label them again by 0 to n minus 1, right? Then this is a unitary transformation of this orthonormal basis. So what the QFT does is it takes each vector of this orthonormal basis, and you get another vector which is a similar superposition of all these computational basis vectors, weighted by the appropriate phase factors. So naturally, if I want to label this as I, if I use the index I to label this, then I have J. Actually, no, I don't want to use I, right? I want to use K. That's what I did. So I used K here. Okay, I did this the other way around. Wait. So let me do the same thing. I always end up making this mess. Okay, so let me say ket K tilde. Okay. Yeah, so I want to call this K tilde, just like I call this YK. So it transforms it to another orthonormal basis, basically, where the elements of this orthonormal basis look like this. So this is again J going from 0 to n minus 1, e to the 2 pi I j k by n, get J, right? So of course, I already told you that this is orthonormal basis and all that, but we can check all of that, okay? So this is what it does to the basis elements of the n-dimensional space. So what about an arbitrary vector? in the n-dimensional space. So if I have an arbitrary vector psi, which is some superposition of the j's, right? So this could be some, let me say x, right? Then after the QFT, this is j going from 0 to n minus 1. Xj are now some complex coefficients, right? So this, I hope you now see the connection emerging between the QFT and the DFT. So this will basically become sum over k 0 to n minus 1, yk, k tilde, right? Where the yk will basically be the discrete Fourier transform of this set of coefficients. So this yk is now sum over, so it's 1 over square root n, sum over j going from 0 to n minus 1, xj e to the 2 pi I j k by n, right? So you have gone from one vector of coefficients. So if I say that x is this vector of coefficients, then what the QFT does is it takes you to another vector of coefficients where y is basically obtained by doing the discrete Fourier transform of x, right? So this is nothing but DFT. And this is the precise statement. Okay. So I hope this idea is clear. So let's now look at properties of this quantum Fourier transform. So the first order of business is to check my claim that this is indeed, that the tilde vectors, which are the vectors you obtain after doing the Fourier transform, whether they are indeed orthogonal, right? So let's check that first. So properties of the QFT, well, I first want to show that J tilde L tilde is delta JL for all J and L belonging to 0 to n minus 1, right? So this is the first property I want to show, which means that the tilde basis, which is 0 tilde, 1 tilde, etc., n minus 1 tilde, is also an orthonormal basis. So let's say we prove this. Of course, I'll do this in the next few minutes. What does this then tell you about the QFT operation itself? What kind of transformation is it? It has transformed you from the 0, 1, 2, 3 basis to 0 tilde, 1 tilde, etc. basis. So what kind of transformation is it?
Unitary transformation.
Indeed. So the QFT is a unitary transformation. It's simply a basis transformation, right? So then obviously one can, any unitary transformation, I should be able to break it down into a quantum circuit, right? And this quantum circuit, that is what we will show on Friday. This quantum circuit has a complexity, or requires only a certain number of gates, right, which goes as n squared, where n is log of capital N. So it turns out that this can be implemented by a quantum circuit which needs only order n squared gates, okay, where n is essentially log of capital N, or in other words, 2 to the n is n, right? Classically, to do the discrete Fourier transform, it turns out that one actually needs something like the order of n times 2 to the n gates. So this is a exponential speed up, and this is at the heart of several exponential speed ups in quantum computation. The fact that you can do the Fourier transform very efficiently with very minimal number of gates. Okay, so let's first show this one step at a time. So let's first show this orthogonality. So check one first, right? So what is this inner product? Please work it out with me. So this is 1 over n sum over k e to the 2 pi I lk by n e to the minus 2 pi I jk by n, right? So this is 1 over n sum over k 2 pi I L minus j k by n. K runs from 0 to n minus 1. What is this? Have you guys done exponential sums like this?
None delta Lj.
Why?
It's the sum of roots of unity. So should be 0 if like L minus j is not 0. And if L minus j is 0, it's just means sum of ones. So
Correct. Okay, good. So this is exactly delta JL, which is what we wanted to show, right? Because like, I don't know who said that, Siddharth, is it? Or who answered? Sorry, I didn't notice.
Amog,
Amok, yeah, okay. Yeah. So if L is equal to J, then what happens? This is just all ones, right? And you're summing over n of them. So that gives you 1. And if L is not equal to J, then you're summing over the nth roots of unity, including 1, right? So that should then give you 0, right? So this is the sum of roots of unity. All right, so this then automatically implies that the QFT is a unitary transformation, right? In fact, you can do better and you can in fact show that the QFT actually, well, okay, no, I don't want to say that, but I want to observe something else actually. So when I go from 0 to this tilde basis, what is 0 tilde? Is that a state that you are used to seeing? I think that's what I want to ask. Yeah. So before we analyze the circuit for QFT, so anyway, once you've shown that this orthogonality holds, then it's a unitary transformation is clear, right? And what we're going to do next time is to work on a circuit for this, but that circuit first requires us to break down the QFT transformation into some kind of product decomposition. So I don't want to start that now. I'll start that on Friday. But before that, we can observe a few more things. So remember that K tilde, so you're going from the basis J to the basis K tilde, right? So what I wanted to ask is what is 0 tilde? So recall that K tilde is 1 over square root n, sum over J going from 0 to n minus 1, e to the 2 pi I j k by n j, right? So what is 0 tilde? Exactly.
uniform
0 tilde.
superposition.
Correct, good, yeah. So 0 tilde is going to be a uniform superposition of all the basis states. This is, if you wish, if you think of the 0 to n minus 1 as a computational basis, right, then this is simply a uniform superposition of the computational basis states. Do we know a circuit to do this? Exactly. So you know that this can actually be done by Hadamard tensor n, right? So you see that the Hadamard gate is actually a special case of the Fourier transform. So that's the first thing that I wanted to observe, that what you do as Hadamard every time is actually a special case of the Fourier transform, right? where it basically does the Fourier transform. It gives you one of the basis states of your Fourier transform, right? Now, of course, we have to have more gates in order to really get to all the other tilde states, right? And that is something we will look at next time. So let me actually stop here because I think the next steps require a continuous, I mean, I will need a good half an hour to do the analysis and the circuit, okay? But, okay, so let me also, yeah, so if I have a single qubit, right? So what I want to say therefore is that if n is 1, right? So if little n is 1, then what is the gate that does the QFT? Just the Hadamard, right? So if in the single qubit case, the QFT is simply the Hadamard, okay? Of course, in the 2 qubit case, it's going to be Hadamard plus something else or followed by something else, right? In the 3 qubit case, it will be more complex and so on. So that's the idea. That's what we're going to do. That sequence is what we're going to build up next time. But just notice that in the single qubit case, the Hadamard gate itself does the Fourier transform, right? Because there's only 0 tilde and 1 tilde. Sorry. Okay, let me stop here. Any questions? All right. So by Friday, your next assignment will also be posted and you'll have 10 days to solve it. And the NSEM exam will be on the 22nd of November. That's the date we have converged on. And I hope that date works for everyone. Oh, do we have a minus sign in the power or does it not matter? It actually does not matter, Nilesh, because that is a distinction between the forward Fourier transform and the inverse Fourier transform. So it's a matter of convention. What you want to call the forward and what you want to call the inverse is just a matter of convention, right? In fact, the phase estimation algorithm will essentially use the inverse Fourier transform. Okay? Yeah. Okay. See you all on Friday then, and well, happy Diwali to everyone.